This is Surveying 1, Lecture 20, and here we are continuing the discussion on measurements, errors, and mistakes. So we covered some of this to kind of renew our focus, even though we touched on this earlier in the semester, and now we're going back and looking at this a little bit more. So just to review, we talked about systematic errors and random errors. I want to point out that very often random errors are referred to as accidental errors or compensating errors, and systematic errors are sometimes referred to as cumulative errors. So be aware that there might be different terms used depending on who's speaking or which book you're reading and so forth. Systematic errors, however, accumulate as we make measurements, and random errors, on the other hand, do not accumulate using those same rules. So if you can imagine that to scale, this is a measuring tool, and we measure, let's say, with a tape or a yardstick, and let's say the yardstick or the tape is long or short, then obviously the error in the true length of that yardstick is going to just multiply as we move on. So if we measure 10 times end to end, we would have exactly 10 times the error. On the other hand, if they're random errors, they're different because they can vary with respect to sign and magnitude. And so we'll talk about that a little bit more. The systematic errors can come from three sources. They can be personal, instrumental, or natural. And basically, if you can understand everything about the system, then you can correct for them. Problem is, we don't always know everything about the system. We think we know everything, so we might miss a few. Hopefully, we don't miss anything that's hugely significant. But one of the things that happens with practicing surveyors, if they're working properly, is rather than saying, I'm going to ignore all systematic errors, they say, which systematic errors are major, I'm going to take care of those, but my error budget, and this is a term that is used in errors analysis, my error budget for this survey is a certain size. I can allow my survey to be of a certain level of accuracy, so I can have a certain amount of error. And because there are certain errors that are very small, I'm just simply going to ignore them. A really common one, by the way, for this has to do with relative humidity. When we use electronic distance meters, we talk about compensating for temperature and atmospheric pressure. On long distances, this can be a fairly important correction to be made. Otherwise, you might have a lot of error in your survey. But there's also an error induced by the relative humidity of the atmosphere. So if it's very moist, it'll be a slightly different reading than if it's very dry. Fortunately, the maximum difference is less than 1 part per million. We often say, well, it's less than a half part per million, so for the kinds of surveys we're doing, we're going to ignore them. But certain agencies might consider that particular error as well. For example, the National Geodetic Survey, when they make measurements over many, many miles, if it's being done with EDM, which is very rare because they would probably use GPS, but if they did so, then they would also measure relative humidity and apply a correction for that. So random errors basically are uncertain as to size. So as you make measurements, your ability to place so again, using a yardstick or a measuring tape, your ability to place the zero end or the beginning end of the measuring tool on the starting point. So let's say there's a starting point right there, and we're going to measure over here to here. So if we place the measuring tool such that the end point is aligned with the start mark, there's always a little bit of inaccuracy. We might be slightly behind, we might be slightly ahead. So there's some random error. Then when we mark where the next point is, the front point, we might be off a little bit because we might be back a little bit, we might be forward a little bit. And every time we do this, there's some of that uncertainty. So finally we get to the final one, and we have that final measurement to make where we might be making a sub-full measurement. And then in addition to not properly aligning the final mark with the marks on our measuring instrument, it may be that we don't fall exactly on a graduation, so we make an estimate. Maybe we break it down into another 10 parts. So instead of just to the nearest 100th, we might measure to the nearest 1,000th, and we might be off a few thousandths in making that estimation. So there's all kinds of errors that can accumulate. The point is with random errors that they're not always the same size. These small errors I talked about, they're not all the same size, and in fact they're not the same sign, because sometimes we're ahead, sometimes we're behind, and so sometimes it has the impact of causing the measurement to be shorter, and sometimes it has the impact of causing the measurement to be larger. Now remember what I've said over and over again, that our standard definition of an error is equal to the measurement minus the true value. So this applies in all situations, and so if the measurement is larger than the true value, then we have a positive error. The measurement is smaller than the true value, we have a negative error, and so on it goes. And then the final thing is that in terms of the size of the errors, is that large random errors are very uncommon. Now it depends on who you are. If you're a surveyor, we say that. If you're a statistician, a person who looks at this as a pure theory, they'll say large errors just occur very infrequently. But what we as surveyors say is large errors are probably mistakes, and we're going to throw them out. And so we often detect them that way by saying, look, here's a really large error that we are pretty sure is not systematic. It may be random, but because it's so large, we're going to reject it and remeasure it or not include it in the average or whatever it is that we're doing. And just like with systematic errors, they can still be from the three different sources. I think you can clearly understand how random errors can come from personal errors. You can also have random errors that occur from nature, because even if you measure a temperature or a pressure or whatever, it's not necessarily consistent. Sometimes it's changing. Sometimes if you're measuring over a long line, there's different temperatures at different parts of the atmosphere between the two places we're measuring and so forth. Or they can be instrumental. In other words, an instrument has its own imperfections. Electronics can be unstable, and it can be that the electronics work a little bit different as temperatures change or as relative humidity changes and so forth. So there can be reasons why an instrument, even if you remove all personal and natural errors from the equation, might still see some fluctuations in the result that they give you if you make enough measurements and you are being precise enough to detect them. So how do you understand how random errors work? Because this is a really important part of surveying. To me, it's fundamental to surveying, and in fact, one of the things that you might be very conscious of is that what we are talking about here is not something that surveyors in practice today all consistently talk about. Part of the reason they don't talk about it is many of them have never been to school and studied this. The other is that it's a little abstract, and so it's easier for them to ignore it. The truth of the matter is it's there all the time, it can't be ignored, and the hallmark of the surveyor of today, and certainly the surveyor of tomorrow, is that they have an intimate understanding of this, even if their boss doesn't. So one of the ways to begin to understand random error and what kind of a role it plays in your life as a surveyor is, first of all, start by imagining that you're going to measure something many times. And I say here, let's say you measure an angle 50 times. Now I know most of you in your right mind would not do that, But actually, we actually will have a lab at some point in your coursework. We will actually have you do that. Make a measurement, maybe not 50 times, or maybe 25 times, so that you can analyze how things vary when you make the same measurement over and over again. Many surveyors think when they measure something, that's all there is to it. The truth of the matter is that it changes for all kinds of reasons. So, first of all, you have to start by agreeing with me that if we make this measurement many times, where you are not cheating, where you're not looking at the display and making it come out the same value every time, that you'll actually get 50 different values. Well, maybe not 50 different values, but lots of different values. Some of the values may be repeated, so maybe you'll only have 40 different values or even 35, but you will have different values every time you make this measurement. So if we average them all, we would get the mean. And then if we subtract the mean from each measurement, we get the residuals. Now remember on the previous slide, I said if we subtract the true value from each measurement, we get the error. So this is kind of a parallel to that, an analogous situation where instead of subtracting the true value, we subtract the mean from each measurement and we get 50 residuals. This is how much each measurement differs from the mean. And remember that these are going to have algebraic signs. So some will be positive, some will be negative, and of course there'll be a few that'll be zero, they'll be right on the average. And you may want to, one of the things that we do as surveyors is that if we see a lot of errors and we look at them, one of the things we start to learn is to have kind of a filter to figure out what to use in your calculations. This is a spelling mistake. This should be throw. So if you see large residuals that seem out of place, one of the things we might do is we might throw them out and then remeasure, make new measurements to replace the measurements that we have thrown out. So one of the things we can do then, and I'm not saying you would do this every time, this is one of the reasons we have computers, but it's very helpful to do this manually to be able to go through this process. So if you list the residuals in order from the largest negative value through 0 to the largest positive, you may see a pattern. For example, that you can imagine that pretty close to half of those residuals will be positive and half of them will be negative. And maybe a few of those might be 0 because they hit right on the average value. Well, that's something that random error theory tells us, that with a large enough number of measurements that we will have an equal number of positive and negative residuals. So now what we can do is take those residuals and we can plot them. We can plot the frequency versus the size and sign of the residual. So let me just do that. So I'm going to draw a horizontal axis here. And on this horizontal axis, I'll mark a 0 point, and everything to the left is negative, everything to the right is positive. And on the vertical axis, I'm going to plot the frequency. So this is how many times a particular size residual occurs. Now, again, imagine doing this, because in a subsequent class, you'll be actually conducting this lab experiment. But if you can think about this, can you see that the amount of residuals that are small are likely to be larger than the amount of residuals that are large? So if you measured, let's say, an angle 50 times and you measured every angle to the nearest 1 second, we could say that maybe we'd only have one angle that's 1 second away from the mean. 10 seconds away from the mean, and that might be the same situation over here. So either plus 10 seconds and minus 10 seconds. But if you look at the angles that are only within 1 second of the mean, we may find that we have quite a few. So here I've drawn 1, 2, 3, 4, 5, and maybe we have 5 on the positive side. and 4 on the negative side. And if we plot these, and we call this a histogram, it's basically a bar graph. We're drawing how many that are within 0 and 1 second of the mean, how many are within 0 and minus 1 second of the mean, and we go off and do that for 2 seconds, 3 seconds, and so forth to 10 seconds. What we would discover is that we'll get something that looks a lot like this. And then if we take a pen and kind of try to draw a smooth curve, we'll get a curve that looks a bit like this. And it's sometimes referred to as the standard normal curve or the Gaussian curve. And it turns out there's a guy named Gauss, a German, who actually came up with this theory. He actually came up with an equation that describes this curve. But this curve is only based on an infinite number of observations. So when we have a finite number, and 50 is actually pretty small, then you might see some jagged teeth on this curve. So be aware that this is what random error theory tells us, and that most of the time our measurements follow this pattern. So what Gauss said is that the area under the curve between the points of inflection is 68% of the total area. So if I go back, I'm going to change my pen color. So if we go back and look at this, it turns out there's an inflection point here and here. What's an inflection point? So this is where the curve turns from being concave down, okay, to being concave up. And if you look at these inflection points, what you'll find out in a curve that follows Gauss's pattern, that each is the same distance away. Now, in my sketch, obviously they're not, but in an ideal curve, they'll actually be the same distance away from the vertical axis. And those points together, when you draw those vertical lines, that if you look at the area under the curve, the part that is cross-hatched here, Gauss said that the area under that curve will be 68.3% of the total area under the curve. And so that number, where it crosses the x-axis, is called the standard deviation. And we always put a plus or minus in front of it, because there is a positive number and a negative number with that value. And just for information, because you'll see this in some books, that the standard deviation is sometimes also called the mean square error, and sometimes you'll actually see it abbreviated MSE. So when we talk about measurements, it's important to realize it's not enough to state just the value. How big is this measurement? So you might say this distance is 438.67 feet. That's fine, but what is the uncertainty in that measurement? And I often do this with surveyors, and surveyors have a hard time because they think I'm asking them a trick question. Obviously, the uncertainty will depend on the technology they used. Did they tape it? Is this paced? Probably not, because we have 0.67. But was it taped? Is it EDM? How did they make the measurement? Was it one measurement? Did they average several? All those things come into the picture. But a surveyor may say that this is good to plus or minus 0.07 of a foot, for example. Well, that makes the measurement a little bit more complete, because you now know the variability that's possible. But even that's not enough, because we also need to have the probability of that uncertainty. So uncertainty is plus or minus 0.07, but it may be that the survey is saying that this is true 90% of the time. So it really takes all three. It takes the measurement itself, the value of whatever was measured, the uncertainty, and the probability to make a complete statement about the measurement. It's not enough to just state the value. So this is something that we don't do as a matter of course in many of our everyday surveys. Many of you who might work for a surveying company would find that if you brought this topic up in your company, that this would be a completely foreign topic and that many would probably not even understand it. And many would not know how to apply an uncertainty value and a probability value to the measurements that they make, whether they're angles or distances or coordinate positions or whatever. But this is a really important part of modern day surveying, and if we as surveyors are going to retain our credibility with the public that we serve, it's really important for us to get on board with understanding these concepts. Why? Because more and more people are starting to understand this, because geospatial data is becoming more and more important. The word geospatial has finally become kind of a normal word in technical circles, in business circles, and you will have more and more people asking you questions about the uncertainty of your measurements and the probability. Now, this is not very different from another group of people we also call surveyors, but sometimes referred to as pollsters. So you may go out and ask a group of people, do you prefer red, blue, or green as the color of your car, or the color of your tie, or the color of your shirt, or whatever it is. And you could take a poll. Sometimes we call it a survey as well. And so this is a different kind of surveying, but when we do this, we may report that everybody in this country likes red, that 30% of the population likes red, and that 40% likes blue, and that actually you might have something like 28% likes green, and then you would have 2% for other, or couldn't make up their mind, or whatever, didn't give us complete responses. This is not very uncommon. And so in a case like this, when a pollster does a survey and reports back on their measurements, this is their measurement. So they're saying 30, 40, and 28, that's the value. Now in their case, it's a percentage, but that's the value. Now if you look at this very closely, especially if it's in print, we'll often see something like that the margin of error for these measurements is plus or minus 2%. And what they're saying is if we go back and do this survey again, we would get possibly a difference up to 2%. So it could be 32, could be 28, could be 42, could be 38, could be 30, could be 26, somewhere in between. And this is similar to the uncertainty their measurement. Now in the case of pollsters, they're making all these measurements in percentages, just like we made this measurement in feet, so uncertainty is in feet. And then you rarely see this, but if you look really hard, you will see one more thing, and that's the probability. And it's not uncommon, especially with things like political polls, for example, prior to an election or something like that. You might actually hear it, not so much on TV or radio, but if you read a magazine article, you might see it, where they'll tell you there's a 95% probability that they're correct, meaning if this survey was done 96 times, or 97 times, or 98 times, or whatever, that there's a small probability, 1 out of 20 basically, there's a 1 out of 20 chance that these numbers are all wrong, and the actual answers are outside of these numbers I've listed here, or the possible uncertainty ranges. And why is that? Because it's what's called sampling. We are doing sampling. We are always making assumptions about the entire population from having examined just a small piece of the entire population, making a survey, a poll of that population. But it turns out in surveying it's the same thing. The whole population would be if we kept measuring and measuring and measuring and measuring. Well, we don't stop. Well, we do stop. So I don't know if this little analogy helps you, but I just threw that in there to help you maybe try to relate to how this applies. This is a concept that can take years for you to properly understand, but it's important to start discussing it right away and for you to start instilling some of that in yourself. So standard deviation, I talked about standard deviation. It turns out that's kind of a natural number. Some of you may know about the term pi. Pi is a natural number. It's simply the diameter of, the circumference of a circle divided by the diameter. It always comes out to the same ratio. It's kind of a natural number. Some of you may be aware of something called the natural number e, which is the base for logarithms. I won't get into here what that means, but there's good reason for it. And similarly, if you use Gauss's equation, the 68% probability number always falls out from doing the calculation, and we'll get into that here shortly. And so standard deviation is often the uncertainty number that we use on data. And in my previous lecture, I talked about how manufacturers will often state that the angle accuracy or the distance accuracy or the positioning accuracy, depending on whether it's EDM or angle measurement or GPS, is stated in terms of standard deviation or 68% probability. But it's also common to see 90 and 95% expressed, and these are simply multipliers that are added to whatever number comes out of the calculation of standard deviation. So where are these on the x-axis? So I said if you take sigma, and by the way, if you haven't figured this out, this transition, sigma it's a lowercase Greek letter, and it's often the symbol used for standard deviation. So in this class, from now on, if I say sigma, it turns out there are two meanings for sigma because there's a capital sigma and a lowercase sigma. But from context, you should be able to figure out that if I use sigma, as I'm doing here, that it means standard deviation. So what you do is if you multiply standard deviation by 1.6449, you get the number that represents 90% of the area under the curve and therefore 90% probability that you will get an uncertainty within that range. And if you multiply standard deviation by 1.9599, you get 95% of the area under the curve, and that's a little bit further out on the x-axis. Now, one of the things that people often do is they'll simply say 2 sigma is 95% error. As you can see, 1.9599 and 2 sigma are not too very far from each other. So they'll often say 2 sigma, whereas 95%, it's actually a little bit more than 95% error. But we often use that just as a simple way of calling out what it is. And then sometimes we call 3 sigma 99% error. It's actually about 99.7% error. But this is the limit sometimes that many of us will use to determine whether an error is an error or a blunder or a mistake. So just to move into that a little bit more, if you line up all the residuals and if any of them are more than 3 or maybe 3.3, some people like to use 3.3 times sigma, then it is common to reject those individual measurements that resulted in such a large residual. And then you either take more measurements to replace the rejected ones, or you have to recalculate the mean and sigma because the mean and sigma incorporate those rejected measurements. So you need to throw them out and then recalculate the mean and recalculate sigma. So here's the equation for standard deviation. And let me just explain again what these are. So sigma, this number here, is the symbol for standard deviation, and it's the lowercase Greek letter sigma. Now it's confusing, but it turns out this letter also is sigma, but that's capital sigma, and it has a different meaning in mathematics. It means the sum of all the numbers that go into a result. And then the next letter next to it looks like a V, and it's fine if you call it a V. It's actually Greek letter nu, and we sometimes spell it this way, nu. So if you want to be educated, say nu, but it's totally fine to call it V because it looks like a V. And V, or nu, is the residual. So if you take every one of your residuals and you squared them and then added them all up, that would be the numerator, the top part of this fraction. And the denominator is n minus 1, where n is the number of measurements. So if we did those 50 measurements, 50 minus 1 is 49, and 49 is what goes into the denominator of that fraction. So that's how we calculate standard deviation normally. Now, many calculators, many scientific calculators, have a function for calculating standard deviation, and it's something that you might want to look for as you go through your professional career. Many of you start with very simple scientific calculators that can do sine and cosine and tangent. Maybe you stop there. But as you move on, looking for a calculator that is capable of deriving the standard deviation is not a bad function to have as well. So that's basically the equation. I'm not going to talk about this anymore, but I have a simple example to talk about. So here's 10 measurements. Actually, this is not 10. I think it's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's a typo. I realized it as soon as I saw my slide. So we have 8 measurements, and those are the measurements. We don't know what it is. It's probably not surveying measurements. It could be we are in a factory, we're making something that has to be a certain length, and we're using a device called a micrometer or a vernier caliper to measure the lengths of these things, and this could be centimeters or inches or millimeters. Could be a lot of things. We don't know what the units are, but this is some of the variation we see in these parts that are being manufactured. They're being injected by a machine, or maybe from some kind of a machine tool, and maybe where there are human beings involved in determining when the process is finished. So the question is, what is the standard deviation? What is the 90% error, and what's the 95% error? So what I have here is simply a blank sheet so I can list out these numbers. So we're going to start by listing these numbers. One of the things you might do, I'm not doing it here, is actually figure out what's the highest and list them in order, because it might sometimes help you see a pattern to the measurements, because this is all part of data analysis. When you get to taking the land surveying exam, you are always expected to be able to do data analysis, and this would be a very simple example of the kind of data analysis you might be expected to do. All right, so if I add these all up and divide by 8, it turns out that the average, which is very commonly written as x with a bar over it, and sometimes even referred to as x bar, it turns out x bar is 3.462. So if we take these individual measurements, so these are the measurements, and in each case, if we subtracted x bar, we would get the residual, or v. And so I'm going to list here the residuals for all these measurements. So it turns out the first measurement is exactly equal to the average, so the residual is 0. The second one, it's 0.005. The third one, it's a negative 0.004. The fourth one is 0.006. Fifth one is 0.010, 0.002 and a negative 0.006. So the interesting thing here is to look at this and see that we have three negative numbers and we have 1, 2, 3, 4 positive numbers. Oops, I'm missing one here. These are not lined up, but so we have 4 negative numbers, 3 negative numbers. It's not exactly 50-50, but it's close because we have a 0. This actually goes out to several more places, and if we went out more places, it may turn out that we actually have an equal number of positive and negative. Keep in mind, the reason you don't get an exact split between positive and negative is that you have a very low number. You may have to do 100 measurements to be able to see that it consistently comes out at exactly 50%. Now, it's not uncommon for surveyors to mistakenly calculate standard deviation with 2 or 3 numbers. And that's a huge mistake because you can't project what Gauss's theories would tell you about those measurements from just 2 or 3 measurements. So you need to have 5 or 6 or something like that before you can even start to make sense of applying these equations. So now if you take nu and square it, I'm not going to write them all down, but I'll just write a couple. So the first one would be 0, second one would be 0.025, third one would be 0.009, and so forth. And we get to the bottom, and I'm going to erase this average here. Let me just write here that the average x bar is 3.462. So the sum of all the sigma square, nu squared, comes out to be 0.001243. So if we substitute into the equation for sigma, it turns out it's the sum of all the residual squared, so it'd be 0.001243 divided by n minus 1. We have 8 numbers, so we divide this by 7, and we get that sigma is plus or minus 0.013. And so this tells us something. Question is what? And so this is a subject for much more discussion in surveying too, but I wanted you to get comfortable with the process of doing this. And what this is telling you basically is how many, if you are plotting a lot of data, this would tell you approximately where the cutoff lies for 2/3 of the measurements. Now these measurements are probably just made up, not from an actual set of measurements, so they may or may not follow the exact error theory. But then if you wanted to calculate 90% error and 95% error, you'd use those same multipliers I had on a previous slide of 1.6449 times sigma and 1.9599 times sigma. It turns out they come out to be 0.021 plus or minus and 0.047. So basically, if we were using 95% as our cutoff, and I like to use 3 times, sometimes I'll use 3 times, sometimes I use 3.5, then what you can do is you look at that number, 0.047, and look at your sigmas to see if you have any sigmas that are that large. And if they're larger than that, then I would reject them and either recalculate the mean and the standard deviation, or I would make new measurements to replace the ones I had thrown out, and again recalculate the mean and the standard deviation from that. So that's kind of the idea behind how you do these kinds of calculations. So now I wanted to move into propagation of random error. So let's say we have 4 measurements we made end to end, like 400 feet, let's say. And let's say that we know that these are brand new surveying students, and so their uncertainty in making 100-foot measurements for each 100-foot length is 5/100ths of a foot. So if they have 5/100ths of a foot in each measurement, and they're basically laid out 400 feet like that, obviously there's 4 opportunities for this 5/100ths of a foot of error, of random error to occur. The unschooled would say, okay, so a total random error in this 400-foot measurement is 0.20 or 0.05 times 4. But it turns out that isn't correct, because sometimes our errors are positive, sometimes they're negative. And also, 0.05 is kind of like the upper limit, and so it could be less. And so sometimes our errors are less. So we use this equation here at the bottom here, that the standard deviation of the total error is equal to the standard deviation of one measurement times the square root of n, where n is the number of measurements. So in this case, n is 4, square root of 4 is 2. 2 times 0.05 turns out to be plus or minus 0.1. So in this 400-foot measurement, our uncertainty, when it comes to random error, uncertainty is always associated with random error, would be plus or minus 0.1. Now here, I use the concept of sigma, but it could be that this is actually 2 sigma or 3 sigma or something else. It doesn't matter, but it would still organize and combine using the same equation, except instead of sigma, we would have sigma sub 95 or E sub 95 to represent 95% error or something like that, different symbols than we've used today, but they still combine this way. So that's a really important thing to figure out. For example, in some of your labs, one of the things that I have done is you measured all the interior angles on a 5-sided figure. Well, how well should they close? So one of the things I do is I say to myself, okay, if you're a professional surveyor, you should be able to measure those angles within 5 or 10 seconds. If you're a brand new surveying student, maybe you're lucky to get them within plus or minus 1 minute. So I would say 1 minute times the square root of 5 to be the kind of the allowable error or the reasonable error that I should expect from you to perform when you combine all your angles and compare them to n minus 2 times 180. Because some of your angles are going to be too big, some of your angles are going to be a little too small. You're not going to consistently be all big and all small. So that would be a reasonable way for me to use random error theory to estimate what the upper limit should be for the errors that you should come up with on your lab exercises. Now, remember I had that last example, the 400 feet. Well, let's say we do this. Let's say we have lab crew number 1 make the first 100-foot measurement, lab crew number 2 makes the second 100-foot measurement, lab crew number 3 makes the third, and lab crew number 4 makes the fourth. And let's say they are all capable of different levels of accuracy. And let's say lab crew number 1 is very experienced and can get it within a 200ths. And lab crew number 2, on the other hand, is really weak and maybe can only do it within 2/10ths. And lab crew number 3 can get it within 500ths, and lab crew number 4 can get it within maybe 0.07. So in this case, we can't combine it the same way, so we combine using the general form of the formula. So what we do is we say the total error in this 400-foot measurement, because each of the measurements has a different uncertainty, would be equal to 0.02 squared plus 0.2 squared plus 0.05 squared plus 0.07 squared, and then we take the square root after we've added all those squared numbers together. And it turns out that this number, or excuse me, this equation is exactly the same as this equation, except that we have simplified it because in the case of this equation, in the previous equation, simply sigma 1 equals sigma 2 equals sigma 3 equals sigma 4 equals sigma n, whatever n is. So just something to keep in mind. So the general understanding with random error is that it accumulates in proportion to the square root of the number of opportunities for the error to exist. And so one final concept, the simple technique for reducing random error. So if you know that you are one of those teams that maybe cannot achieve consistently very high levels of reliability in your measurements, that your random error is quite large for whatever reason, then one of the ways you can improve it is to measure something more than once. So we often refer to this as redundancy. So there's a redundant part where simply measuring something more than once, especially if you don't repeat exactly the same steps over and over again, is that you can detect blunders or mistakes. But if you have a number of measurements, let's say you can measure something to plus or minus 2/10 of a foot, but you need to do better. So if you take the same crew, they measured it once, it's plus or minus 0.2, but if they measured it 4 times and then took an average, what you would do is you would put 0.2 in for sigma sub once and divide by the square root of n, which is 4. So you divide the 0.2 by 2 then, the square root of 2, and you would get 0.1 as the uncertainty in your measurement. And this can go on. So if you measure it 9 times, you can now divide 0.2 by the square root of 9, which turns out to be 3. So you get 0.2 over 3, which comes out to be about 0.07 feet and so forth. So this is how it is very common practice in surveying, whenever you want higher reliability in your measurements, to make that measurement more than once. So 2 is actually a very bare minimum. In fact, the only reason in the labs that you've been conducting you measure something twice is to make sure that you don't have a blunder. It's really not that helpful in improving the reliability of the measurement beyond eliminating possible blunders. But when you get up to 4 times and 6 times and 9 times and 16 times and so forth, you can make considerable impact on the measurements that you make. So that pretty much wraps up this discussion on measurements, errors, and mistakes, and we will end it here.